Hi guys, today we're going to be discussing the topic of ionization energies. So the first thing that we're going to be doing is we're going to be looking at the definition of the term first ionization energy. So the first ionization energy refers to the energy required to completely remove 1 mole of electrons from 1 mole of gaseous atoms. Now it's very important for these atoms to be gaseous, and we're going to discuss the reason later. Forming 1 mole of univalent means the charge is 1, positively charged ions. Now this is the equation for first ionization energy. As you can see, you have 1 mole of gaseous atoms, and this 1 mole of gaseous atoms is going to lose 1 mole of electrons to produce 1 mole of univalent positively charged ions, like we talked about in the definition above. So this was the definition of the term first ionization energy. Now the more the first ionization energy, or the more any ionization energy, the more difficult it gets to remove electrons from your outer shell. Now this is second ionization energy. So in this case, you have 1 mole of univalent positively charged ions, and 1 mole of electrons is going to be lost. So at each stage of ionization energy, be it first, second, or third, the amount of electrons that are going to be lost is going to stay the same. Only 1 mole of electrons is going to be lost. What's going to change is the charge on the ion. Now if it's first ionization energy, the charge is going to be 1. If it's second ionization energy, the charge will be 2. And if it's third, the charge will be 3, and so on and so forth. So the charge on the ion is going to stay the same, but the amount of electrons that it loses, the charge is going to be different, but the amount of electrons it loses is going to be the same. And the reason why the particles need to be gaseous is because they're not going to be influenced by their neighbors or held together by any bonds. If it was solid or liquid, there would be more intermolecular forces which would prevent them from the electrons from being lost. The next thing that we're going to be discussing is the trends in ionization energy. Now this is divided into 3 parts. And the first part is successive ionization energies. So this is an element. At this stage, it didn't really matter which element it is. Now, these blue circles over here represent the electrons, and the green circle represents the nucleus. And I've drawn the simple O-level structure, so these circles over here, the white ones, these just represent the orbits. So now the electrons that are in the inner orbits are going to be different in this case. And the electron that's named B over here in the outer orbit is also marked over here. Now B is going to feel less nuclear charge. Why? Because it's shielded from the full nuclear attraction. Now what exactly is shielding? Shielding is basically when over here, this is the nucleus, right? And this is positively charged. So these inner electrons are actually going to experience a greater nuclear charge. Why? Because they're closer to the nucleus as compared to electron B, which is further away. So because of that, it's going to be shielded from the nuclear charge. So this layer of electrons is actually going to act as a shield. So the amount of charge that's experienced by B is going to be lesser than the amount of charge that's experienced by these inner electrons. So all of the electrons that are in the outer shells, in this case there's only 1 of them, but let's just say there were 2 or 3, all of those were going to be shielded from the nuclear charge by the electrons that are in the inner shell. And the rule of thumb here is that the further out an electron is, the less energy is required to remove it. Now, this thing that we're talking about, successive ionization energies, refers to the ionization energy in just one element, like within the element only. So let's take a look at an example. Over here you have magnesium, and here's the electronic configuration for magnesium. Now, if you're confused about how to write electronic configurations, there's a video on that, so you can go check that out. So you have 1s2, 2s2, 2p6, 3s2, and 3p2. Now in this case, if you take a look at the ionization energies, the first ionization energy is going to be 738 kilojoules per mole. And this is the ionization energy required to remove this electron over here, which is going to be in the 3p orbital. The second ionization energy is 1451 kilojoules per mole. Now as you can see, the ionization energy is increasing. Why? Because this electron is going to be shielded by less electrons as compared to this electron, which is going to experience more shielding because it has one more inner electron shielding it. So basically the second ionization energy removes the electron that I'm marking right now in red. And the third ionization energy is 7733 kilojoules per mole. As you can see, there's a huge jump over here. There's an almost 7 times an increase. So when you're removing this electron, the increase is going to be much, much greater. And the key over here is to find that big jump if you want to determine what group it's in. As you can see, the great difference in the ionization energies is between the second and the third. So that shows to you that this is going to be in the second group because it's going to experience a lot less shielding because it's in a completely different orbital. So when your electron moves to a different orbital, there's going to be a big jump in the energy levels. And that's going to help you determine what group it's going to be in. And in the next slide, we're going to cover another example related to this to make it easier for you. So normally in MCQs, they might just tell you there's this imaginary element or there's this element called X. And they might just give you the first 5 ionization energies or the first 2-3 ionization energies for this element. In this case, you have 631, 1235, 2389, 7089 and 8845 written over here. So as you can see, the big jump in this case is over here. The difference is around 3 times or more than 3 times. So in this case, you're going to look at this group over here. So this element is going to be in group 3. So the amount of valence electrons that you're going to have is going to be 3. Why is that? Because there's a huge jump between the third and fourth ionization energies, which tells you that somewhere over here the valence electrons are being removed. So because of that, it takes a lot more energy to remove the fourth electron because the valence electrons, the ones that are in the valence orbital, have been removed. So because an entire orbital has been removed, the amount of shielding that's going to be experienced by the inner electron is going to be a lot more. So because of that, the element is going to be in group 3. And if you draw a diagram in which you have the number of electrons that are being removed on the x-axis, and if you have the ionization energy marked on the y-axis, you're going to see that there's a huge jump between the second and third. And the reason for that has already been explained. After the trend in successive ionization energies, the second trend that we're going to be talking about is the trend in ionization energies down the group. So in this case, we have group 1 marked over here. And if you look at the electronic configuration, you can clearly see that at least for the first 3 elements, and even if you go down, even if I haven't marked it, you're going to be able to tell that the number of shells is slowly increasing. And because of that, the ionization energy decreases. And in the next slide, we're going to discuss the reasons behind this. As you go down the group, your proton number is going to increase. And like we saw in the previous slides, the number of shells are going to increase. So you're going to have more complete shells. And so the outermost electron is going to be more shielded. And we discussed the concept of what shielding is in the previous slides from the nuclear charge. So since it's going to be more shielded, the ionization energy is going to be less because less energy is going to be required to remove that electron.